Hi class, and today we will be starting chapter 6, which is proportions in chemical compounds, and our first section in this chapter is chemical proportions and percent composition. Now, I have included in your Teams thing the handout for you. If you want to print that off now, and you can fill it in as we go along, you may pause the video at any moment to fill in the gaps in your presentation slides. So we first look at chemical formulas. And when we have a chemical formula, we actually can determine the percentage composition of each element present just by looking at the chemical formula. We go from the formula and we can determine percentage composition. So that basically is what percent of each element makes up the total mass of the compound. Then we can also experimentally determine the mass of each element in a compound. And when that is done, you can actually calculate the percentage composition, and from that determine what the chemical formula is. So using mass data, we can calculate percentage composition, and then we can determine a chemical formula. And these all have useful applications, which I will talk about in our next lesson. So in this section of the book, we are looking at three things specifically. The first, we're going to be looking at compounds that contain the same elements in the same proportions. Then we will look at compounds that contain the same elements, but however, they are in different proportions. And then we will look at percentage composition, what that means, and now the elements in a compound, and determine what percent of each is in a compound. So we look first at compounds that contain the same elements in the same proportions. So the basic principle is that whenever you have a compound and you know exactly what it is, that chemical composition will not change. So water is always H2O, always 2 parts hydrogen, 1 part oxygen. It does not matter whether the water is a solid, liquid, or gas. It will always have 2 parts hydrogen, 1 part oxygen. It doesn't matter whether the water is on the Earth or the Moon. Water will still be H2O, or whether it's found naturally or made in a lab. Now this is defined as the law of definite proportions. This was developed by a French chemist, Joseph Louis Proust, and he discovered this all with samples of copper 1 carbonate. And he noticed that they had the same proportions of copper, carbon, and oxygen by mass, no matter what their source was. And he came up with this law, and this law is defined as chemical compounds always contain the same proportions of elements by mass. Next, we will look at what that means when we do calculation. And so we're going to talk now about mass percent. And mass percent is defined as the mass of each element in a compound expressed as a percent of the total mass of the compound. And you already know this and are familiar with it because you know percentages. If you think of a percentage on a test, your percentage is the amount of right answers divided by the total amount of questions multiplied by 100%. So basically all we're doing is calculating percentages, much like you calculate the percentage mark on your test. And an example of this is what I call a jelly bean example. Very simply, the question is, what is the percentage composition of yellow jelly beans in a mixture that contains 35 yellow jelly beans and 15 green jelly beans? And what is the percentage composition of green jelly beans? Simply, the percentage of yellow is the 35 yellow divided by the 50 total, which is the 35 yellow plus 15 green, times 100%, which is 70%. Then very simply, the percentage of green, you can take the 100% total minus the 70%, that's yellow, and that will give you your 30% green. Or you can also do it by taking your 15 green, dividing it by the total of 50 jelly beans, which are yellow and green combined, times 100% to get 30%. So now let's look at this and apply it to a chemical situation. When we do that, we'll do water, for example. And what we'll do is calculate the mass percent of hydrogen in water. First, we calculate the molar mass of water, and this is what you learned in lesson 5.2, how to calculate the molar mass of water. And if you remember, the molar mass of water would be equal to 2 times the molar mass of hydrogen, because there are 2 hydrogen molecules in the water, plus 1 molar mass of oxygen, because there's only 1 oxygen molecule in water. So if you go ahead and calculate that, you can either pause it or you can watch. Looking at your periodic table, you look at the molar mass, and so you multiply 2 times the 1.01 grams per mole for hydrogen. You look at oxygen, it's 16 grams per mole, and there's only one of those of oxygen. You plug it into your formula, and you get 18.02 grams per mole. So that is your molar mass of water. That is your total. That will be on the denominator or the bottom of your fraction when you go on to calculate your mass percent of hydrogen in water. So in order to calculate the mass percent of hydrogen, you take that mass of hydrogen and divide it by the total mass of water times 100%. So here is the formula, just written out now in a formula way. And when you plug in your numbers, just keep in mind that mass of hydrogen on the top, you have to take into account there are 2 moles of hydrogen, so you have to do the 2 times 1.01 on the top, divide by your total mass of water, which is 18.02 grams times 100%. That means, and it equals 11.2%. So that means of the total mass in water, 11.2% of that mass is hydrogen. So we'll look at another example, and this comes from your textbook. This comes from practice problem number 2 on page 260. You can either pull out your textbook and look at it now, or you can just follow along here. So it says, calculate the mass percent of oxygen in dinitrogen tetroxide, which is N2O4. So first you have to calculate the molar mass of N2O4. You want to pause the video now, you can do so and calculate it and then check with my calculations. So remembering that the molar mass of N2O4 will be 2 times the molar mass of nitrogen, because there's 2 nitrogen molecules, plus 4 times the molar mass of oxygen, because there's 4 oxygen molecules, or atoms, sorry. Plug in your values. So 2 times 14.04 grams per mole for nitrogen, plus 4 times 16 grams per mole for oxygen. That gives you a total of 92.02 grams per mole. Now, I haven't said anything yet about significant digits, but if you notice here, your answer will have 4 significant digits, and that's because your nitrogen has 14.01, has 4 significant digits, and also your oxygen also has 16.00, which is 4 significant digits. So your answer will have 4 significant digits. Now, in order to calculate the mass percent of oxygen, you have to take the mass of oxygen divided by the total mass that you just calculated of N2O4 and multiply by 100%. So again, you can pause the video now and do that, and then check with my calculations. So the formula is mass percent of O equals the mass percent of oxygen divided by the mass of N2O4 times 100%. Remember again, your mass of oxygen has to take into account that there are 4 oxygen atoms in the molecule. So that's why you've got 64.00 grams on top for your mass of oxygen, divided by the 92.02 grams for your total mass of N2O4 times 100%. Gives you 69.55%. Again, 4 significant digits, because both your values in your calculation have 4 significant digits. We'll look at another problem, and this is actually even a bit simpler. These ones have involved calculating the molar mass given your chemical formula. But if you're just given the mass, it is very straightforward. And your example is practice problem number 3 on page 260, which states a 650 milligram sample is analyzed and found to contain 51.0 milligrams of hydrogen. What is the mass percent of hydrogen in the sample? Again, pause the video, see if you can calculate this on your own, and then check with my work. So your formula would be mass percent of hydrogen equals the mass of hydrogen divided by the total mass of the sample times 100%. You are given that the mass is 51.0 milligrams. The total mass is 650 milligrams. Take 51 divided by 650, multiply by 100%, and you get 7.8%. Your answer has 2 significant digits. That's because your mass of hydrogen, 51.0, has 3 significant digits, but the total mass of 650 milligram only has 2. The 6 and 5 are the only significant digits, so that's why your answer contains 2 significant digits only. And we'll look at one more practice problem, a little bit more involved just because it involves the comparison of 2 compounds, and it is stated as, which substance has the greater mass percent of sulfur? Sulfurous acid, H2SO3, or peroxydisulfuric acid, H2S2O8. If you look at that, can you figure out or guess what you think the answer would be? Well, you can go ahead and calculate. First, we'll look at one compound, then the other. First, you will calculate the molar mass of H2SO3. You can go ahead and try that. And it would involve taking the molar mass, which would be 2 molar mass of hydrogen, 1 of sulfur, 3 of oxygen. You look at your periodic table and plug in the appropriate values, and you get this for a total of 82.09 grams per mole. Once you have that, then you go ahead and calculate the mass of sulfur, because this is what we're looking at, the mass percent of sulfur divided by the total mass. And there is only 1 mole of sulfur, so it's 32.07 grams divided by the total mass of 82.09 grams times 100%. So in H2SO3, the sulfur makes up 39.07% of the total mass. Now we will do the same thing for the H2S2O8. And again, you calculate the molar mass. So again, you have 2 moles of hydrogen, 2 now of sulfur, and 8 of oxygen. You plug in your values from the periodic table, and you get a total molar mass of 194.16 grams per mole. So to find the percentage of sulfur in that, you take the mass of the sulfur, divide them by the mass of the total mass of the compound times 100%, remembering that there are 2 sulfur atoms. So you have to do 2 times 32.07 grams per mole. So you get 64.14 grams divided by the total of 194.16 grams times 100%. And that means in this compound, sulfur only makes up 33.03% of the mass. Now you compare the two. Since the mass percent of sulfur in H2SO3 is 39.07%, in H2S2O8 it is 33.03%, we can conclude that the sulfurous acid, H2SO3, has the greater mass percent of sulfur. So go ahead, pause the video, and try these problems on your own from the same section, page 260, numbers 4, 6, and 7. And if you have any problems, just get in touch with me and I can help you with that. And once you're done, we can carry on with the video. Just press play and keep on going. All right, we are going to now look at compounds that contain the same elements in different proportions. And it's just briefly, you would do the same kind of calculations based on the chemical formula or based on mass. But we're just going to note a few things under this heading. That ionic compounds always contain the same elements in the same proportions. We've talked about that before earlier in the course. But we do know that there are many other compounds that have the same elements in different proportions. And that gives them their different chemical properties. And even just this simple example of NO2, nitrogen dioxide. It's emitted from combustion engines. It's highly toxic. It has 1 nitrogen, 2 oxygens. But if you change the proportions and you have 2 nitrogens and 1 oxygen with dinitrogen monoxide, this is a gas used during dental procedures to help calm patients. Very different chemical properties just because they have different proportions of the elements. So we're going to take a moment now and look at percentage composition. And percentage composition can be determined from the mass data. Percentage composition itself, if you look at your textbook, the definition of percentage composition is the percentage by mass of each element in a compound, and it will equal 100% when added together. So basically, it is just determining the mass percent of every single element in a compound, not just one. And then summing them all up together, they should equal the total of 100%. So when we use mass data, we're taking experimentally determined masses, and we're just using that data to figure out the percentage composition. So, first of all, the masses of the elements are measured, and then the mass of the entire sample. Now, this can be done experimentally, and we will be doing a lab with this with magnesium oxide and determining the percent composition of magnesium oxide. Your problems, though, will give you the masses, and then you have to determine it from it. And what you do then, once you have the masses, you calculate the mass percent, which is what we just learned, of all the elements then in the compound sample using the data. So here is an example. A sample of a compound that is found in gasoline has a mass of 35.8 grams. The sample contains 30.10 grams of carbon and 5.70 grams of hydrogen. What is the percentage composition of the compound? So basically the question is saying, okay, you have this compound, what percentage is carbon and what percentage is hydrogen? You just want to know the mass percent of every element that is present. So first of all, you calculate the mass percent of carbon. Again, you can pause the video and try this on your own. But we do know that the mass of carbon will be divided by the total mass of the sample times 100%. We are given that the mass contains 30.10 grams of carbon. The total mass is 35.8 grams. Multiply by 100%, and you get 84.1%. Again, notice the significant digits. The mass of carbon has 4 significant digits. The total sample of 35.8 only has 3, so your answer only has 3. Then you can go ahead and calculate that for the hydrogen. And again, you plug in your mass of hydrogen, which is 5.70 grams, divided by the total mass of the sample, which is 35.8 grams, times it by 100%, and you get 15.9%. Now, one way to check your work is to add your two numbers together, or depending on how many compounds you have, the total should be equal to 100%. And then we can conclude that the percentage composition of this compound is 84.1% carbon and 15.9% hydrogen. So looking at now practice problem 19, on page 264, has a volatile chemical was removed from a crime scene. Analysis of a 35.20 milligram sample of the chemical showed that it contained 3.56 milligrams of carbon and 0.28 milligrams of hydrogen. Later, investigators learned that the chemical was chloroform, CHCl3. What is the percentage composition of chloroform? So when you're asked percentage composition, you need to do the mass percent calculation for each element involved. So you're going to have to do it for carbon, for hydrogen, and also for chloroform. Notice that you are not given the mass of chloroform, but you can figure it out. We'll start first, though, with the mass percent of carbon. Again, take your mass of carbon, divide by your mass of your sample, times it by 100%, and you end up with 10.1%. So you can pause the video and go ahead and do it for hydrogen. The mass percent of hydrogen is the 0.28 milligrams of hydrogen divided by the 35.20 milligrams total of the mass sample times 100%, and you get 0.80%. Now, if you want to go ahead and do chlorine, there's a couple ways to do it. Probably the simplest way is to actually just take 100% and subtract the other percentages you've calculated, because everything else is going to be chlorine. So you can do 100% minus the 10.1% from carbon and minus the 0.80% from hydrogen, and that'll give you 89.1%. You could also take the 35.20 milligram sample, subtract the 3.56 of carbon, subtract the 0.28 milligrams of hydrogen, take that answer, divide it by 35.20 milligrams, times it by 100%, and you're going to get 89.1%. So you can conclude the percentage composition of chloroform is 10.1% of carbon, 0.79% of hydrogen, and 89.1% of chlorine. So you've seen a few samples of these percentage composition. Remember, these ones mean, these questions that say, what is the percentage composition, just means you calculate the mass percent of each element in the compound. So go ahead and try page 264, numbers 11, 17, 18, and 20. And that is your lesson for today. I hope you have a good day.